So obviously, one of the most important fluxes at the air-sea interface is water itself through evaporation and precipitation. So for an ocean model, forced ocean model is what we typically say. You also need hydrological boundary conditions which have to satisfy two things. One is how salinity is affected by the evaporation and precipitation, and the water budget itself. So for temperature, it's simpler in a couple of ways. One is, of course, just the heat is being exchanged, and the other is that when there is a warming or a cooling, there is a direct impact on the atmosphere. There are details, but let's just remember that when the ocean warms, the atmosphere responds, or when the ocean cools, the atmosphere responds. So hydrological boundary conditions get complicated basically because of these two things, that salinity is left behind and salinity change does not directly produce an atmospheric response, unlike the temperature change, which does, right? So the density of the ocean water is seawater is of course a function of temperature and salinity, because we typically ignore the dependence on pressure and consider it to be an incompressible fluid. We write the density as some background density times a temperature expansion coefficient and a salinity effect plus some nonlinear effect in terms of T minus T0 squared with some coefficient gamma. The values are given here, but essentially this means that when temperature warms, this is a negative coefficient here, so the density decreases, whereas beta is positive, so when salinity increases, density increases. So you can see the opposite direction of the correlation there. So the standard density is 1028 kilogram per meter cube. Temperature T ocean T0 is set typically to the equation is based on a relation developed around 0 degrees centigrade and mean salinity of 35 practical salinity units PSU, or often we just mention salinity without any units. Alpha here, the thermal expansion coefficient, is minus 5.4128 times 10 to the minus 5 per Kelvin, so that's how density gets affected. Beta is 7.623 times 10 to the minus 4. That's how salinity affects the density. And gamma here, quadratic term, is minus 5.0804 times 10 to the minus 6 per Kelvin squared. So typically, if you are looking at either the differences with temperature perturbations or with temperature change from one place to another and so on, you can see how density changes can be estimated. So to look at the differences in the time scales of salinity, temperature, and the air-sea interactions with temperature change and salinity change, we can remind ourselves the Newtonian relaxation kind of approach we used. Newtonian cooling, often it's referred to as. So if you have a prescribed temperature T star ocean that you are driving towards T ocean, so you can think of it as an equilibrium solution. Depending on the process and the time scale, this can be anything, but typically what you do is you try to run the ocean model to equilibrium so that you can then do perturbation experiments on top. So it's a question of how long it takes for the ocean model to be forced with, let's say, an annual cycle of heat flux, annual cycle of salinity flux or hydrological boundary condition, and the annual cycle of wind stress and so on. And that allows, once you reach equilibrium, it allows you to look at other processes of how mixed layer heat budget at any particular place is determined, or how the relation between salinity and temperature distributions are affecting ocean circulation, and so on and so forth. Okay, so the flux ocean to atmosphere in heat was dependent on ocean temperature with the coefficient D star that drove a relaxation towards the difference of ocean temperature with the prescribed temperature, which is straightforward in the case of heat flux, because as we said, a perturbation to temperature produces a atmospheric response, but it's not the same for the salinity. So you can still write salinity flux from ocean to the atmosphere as some coefficient times S minus S star, where again S star is, let's say, a prescribed salinity distribution like a climatology. Again, you can derive a time scale here similar to temperature, rho delta Z or ds star, where delta Z is our, let's say, depth in our one box model that we looked at. So that gives you a relaxation time scale. Of course, the problem is we have to also balance water mass, so or volume, depending on what approximation you are using in these things. So flux of water from the ocean to atmosphere in terms of humidity is again a coefficient d star w times q minus q star, where q star is the specified humidity and q is the transient. So there is a temperature dependence here that is always implied as you are integrating forward in time. The additional constraint is that the freshwater budget, P minus E, how much is evaporation taking out of the ocean and how much is precipitation putting back. You can do it at, if you do it in a one box, obviously you have to worry about global P minus E as well, but let me not go there. So that is 1 over rho S ocean times Fs flux of ocean to atmosphere of salinity. Okay, so you can imagine that there is actually no salinity leaving the ocean into the atmosphere in this sense. There is sea salt and other things that are not directly related to what we are talking about here. So you are equivalencing freshwater flux to a salinity flux. That's a big difference in terms of heat exchange versus freshwater exchange. And in this case, independently, there is evaporation happening depending on the vapor pressure and latent heat, coefficient of latent heat exchange, and precipitation is rho L times P. Sorry, this is evaporation, this is precipitation. That's the energy exchange associated with evaporation and precipitation. So I hope the point is clear. When you look at distribution of water fluxes P minus E in meter per year at a contour interval of 0.5 meter per year, the map is compiled from data by Benno Blumenthal of Columbia University. Unfortunately passed away at a very young age because of brain cancer. Dear friend, incredibly nice person, very smart person. Where numerous data sets are available, so you can go to this website. So you can see again, this is where precipitation exceeds evaporation. That's our ITCZ, SPCZ, Indian Ocean, complicated picture, ITCZ here, or the Atlantic and mid-latitude storm tracks, and then you have evaporative subtropical gyres that are typical, and so on. So model has to match salinity, but we have to also make sure that the water balance is maintained, just like for hydrological models on land, right? So hydrology of the ocean is important as hydrology of the land as well. So this is for the Atlantic in meter per year. So how much excess rain is happening in the IPCZ above the evaporation, and where evaporation deficit is compared to the precipitation, and again surplus regions here. Okay, this is a very unique situation because of the Gulf Stream, freshwater formation, and so on. But here we have differences as we go to the Southern Ocean. Okay, so oops, I think I lost some points here. No, I didn't. Okay, so I will do momentum budget quickly and then come back to mixed boundary conditions after this to say how we deal with this difference in salinity flux versus heat flux. Okay, so momentum flux is fairly straightforward in terms of formulation, where you have wind stress given by some drag coefficient times density of the air times the magnitude of wind vectors, so Vh squared, where Vh is of course square root u squared plus v squared. And with the wind tunnel experiments in the lab, drag coefficients are estimated based on the stability parameter and so on and so forth. There are details. So if wind speed is less than 6 meter per second, this amounts to 1.1 times 10 to the minus 3 with the appropriate units, whereas if wind speeds are greater than 6 meter per second and less than 22 meter per second, obviously that means you rule out a lot of the cyclone hurricane situations, then it looks a bit more complicated. And this tells you again what we talked about before. In the models, there are primitive variables like winds, temperature, humidity that are computed by the equations, by the system of equations, by the climate model. But to transfer that information into ocean atmosphere fluxes or other purposes, we have to convert them to wind stress and so on, which are evaporation, freshwater flux, which require parameterization. So this is basically a parameterization. So do these values really hold also in the open ocean in the real world? Not so easy to determine, because these are typically only measurable in a lab. So that always is something we have to remember. Okay, so let's leave it here with the important message in mind. For the wind stress, there is also the issue of how deep the momentum penetrates into the ocean, just like we have to worry about how deep the solar radiation penetrates and how deep the heat flux exchange happens. We assumed 50 meters in the previous example, but these are not very easy issues to measure or represent in the models. Okay, we know that upper ocean is responding rapidly to momentum and heat flux exchanges, but what is that exact depth? That's not always very straightforward. So all those uncertainties go into the ocean model, but we'll come back and look at how to deal with this so-called mixed boundary condition, where we deal with the difference in the way heat is exchanged, and salinity flux has to be computed considering the freshwater flux and its impact on salinity in the ocean. Okay.